right. Hello, class. I'm Nicholas Szostek,
I'm Michael Paiva.
and this is our capstone project. All right.
So we are making an ammeter to update the current analog ammeters in use today for automotive applications. These ammeters that are in use today have worked great, but have their drawbacks due to technology that they are based on. Current ammeters use a needle and pointer display and are limited in functionality.
We propose that we will make an updated ammeter for automotive applications. It will accurately measure the current. It will be digital, that displays on an LED pixel display. We also propose that our ammeter will have non-volatile memory for stored data for later use with bar graphs with the max current output. There are similar solutions, but they all still use PMMC technology. While still great, we intend to update this design to what we see fit. There are no ammeters that store measured data on the market, which we propose that we will introduce to our design as well. And here is a picture of the current ammeter models, which we intend to update with a digital display. Although good in their practicality, we want to update the models.
The idea behind our ammeter came from because I am currently building a Jeep for off-road use and have found in the past that current ammeters are difficult to read, especially when traveling at speed or on rough terrain. Also, I found that unless I was constantly staring at the ammeter, I was likely to miss current spikes caused by high power audio equipment or lights or anything like that. Something that could be potentially damaging to the alternator. I've seen people that employ this type of equipment will either replace the alternator before they go for a trip or carry a spare alternator with them.
This project has great importance to us because this is the last project that we will be doing as we transition from student into engineer. And we get to show everything that we have learned during our education at National. We could possibly expand this project by including voltage and temperature monitors, or we could also expand it to have a full alternator monitoring system throughout the car.
These are our marketing requirements, which are that it needs to measure accurately, needs to store and give a means to retrieve that stored data, and needs to be easy to use.
And here is our objective tree. Our objective tree, we break it down into each component in our design that we propose. We want it to be easy to use with plug and play capabilities, intuitive controls, and a clear display. We want it to measure accurately with precision shunt resistors, bad alternator detection, and a high resolution ADC. We want the ammeter to have a mechanism to retrieve stored data with either a Bluetooth connection or a micro SD/USB port. And lastly, we want it to store the measured data with non-volatile memory.
Here we ranked our marketing requirements, and we can see that accurate measurements are the most important requirement, followed by data storage and retrieval.
The basic theory behind an ammeter is used to measure the strength of the current flow in a circuit while connected in series. Ammeter's current will flow through a coil, and the electromagnetic field around it will generate enough torque to move the needle to the measured amps on the display. When doing calculations for an ammeter, we just need to use basic ohm laws to achieve the output. They must be measured in series due to current of interest that will go through the circuit. The only way to work around this is using a shunt resistor, which you can put in parallel if it exceeds the ammeter's limit.
As Nick said, a shunt resistor is used to measure large current. The main drawback for a shunt resistor is its large power dissipation.
And here's an example of a shunt resistor ammeter that is multi-range in capability. It makes use of different valued shunt resistors to acquire the range that is needed out of a single ammeter instead of just having one range.
This is a more modern ammeter based on the current standard technology. It has a digital display, but still uses a permanent magnet moving coil with all of the current flowing through the ammeter.
There are some current limitations of ammeters on the market today. Mostly what is still being used is the permanent magnet moving coils, and most are not LED displays. They're still the analog that you saw on the couple slides back. The similarities between our products and current products is that they are both designed to measure the current drawn from the alternator. Some ammeters on the market do have LED displays that are more updated, like we propose to incorporate.
These are our problem statements. We need to improve ammeter. We need an improved ammeter capable of completely monitoring current draw through a vehicle with an easy to read display. Ammeters have worked great for this long, and now it's time for an update.
All right, here is our requirement specification table. You can see where each of our marketing requirements match up to the engineering requirements along with our justifications for each. We want the system to measure with at least 1% accuracy, which is crucial to competitive marketing. The display should be drawn down to 0.01 amps. We also want a micro SD port for data storage, and we want the system to store data at 1 Hertz. You can see the correlation between the marketing requirements and the engineering requirements and the justifications for each in our table there.
This is our trade-off matrix between engineering requirements and the marketing requirements. From the matrix, you can see the arrow indicates the correlation and two arrows indicate strong correlation. From this, we can see most items have a positive correlation except overall dimension. That's easy to see because adding more functionality increases the size, and a smaller size is more desirable.
Here's our engineering trade-off matrix. As Michael said before, the arrows indicate correlation, and 2 means that that is a strong correlation. The display still has a lower correlation compared to the rest, as Michael pointed out before in our trade-off matrix between engineering requirements and marketing requirements.
This is our self-assessment for the engineering requirements, and you can see that we feel the requirements are done well.
This is our team building process. During our team building process, we decided that we came up with the name of Paiva and Szostek aftermarket ammeters. Our mission objective is to design and prototype out a digital ammeter that will monitor the current drawn from an alternator in a car. Our ammeter will have capabilities for you to read and save the output of the readings at your disposal.
These are decision-making guidelines, which state that the leader will make all decisions after discussion with the team and that no opinion will just be dismissed.
All right, and then we came up with some meeting guidelines. We've set these specific meeting guidelines for our group for each week going forward and throughout the course. We have meetings about 4 to 8 times a week, just depends on our schedule, and we always have an agenda for each meeting. We record each meeting so we can always go back for references just in case if we forgot what we talked about. And we always listen to each other's thoughts and ideas and not just brush it to the side since we are a team.
These are the team roles. Nick will be the software engineer, optimist, and spokesperson. And I will be the leader, the analyst, and the pessimist.
All right, for our conflict resolution, when solving it, we will listen to each other after whatever we say about the product. We have set out ground rules to resolve issues within our team, and we have also chosen to always identify each other's concerns to each other throughout this course and design.
This is our team self-assessment. And we can see that we are pretty comfortable with our team and wouldn't really change anything about it.
Right. This is our concept fan that we have came up with that shows each of the way that we can go about this project moving forward. We will have to decide to either use the shunt resistor or the Hall effect sensor in our design.
This is our concept table, which just shows the possibilities for our proposed ammeter. It's worth noting that there are only two ways to measure current, which Nick just touched on, and that's either the shunt resistor or the Hall effect sensor.
And here is our strength and weakness table for the Hall effect sensor and shunt resistor. You can see that each method has given takes on both sides. The shunt resistor has a high power dissipation, but is accurate and inexpensive. The Hall effect sensor has a wide range of current reading capabilities, but they are expensive and not very accurate when they're taking their readings.
This is our concept selection matrix. We compared our proposed ammeter to a readily available aftermarket ammeter and decided to pursue the shunt resistor design. The best benefit of the shunt resistor design is the accuracy it affords.
All right, here is our level 0 design. That is our ammeter. You see that we have three inputs, which are the current flow, the brightness control, and the power supply. And there is one output, which will be on the LED pixel display. Here is we have a breakdown of our level 0 design of our ammeter that will display the current drawn from an alternator in any car. As I said before, the inputs will be the current that is flown from within the vehicle, the power supply that will be 12 through 15 volt DC, and the brightness control for the pixel display. The output will display the current drawn down to 0.01 amps.
This is our level 1 functional design. You can see we put in the shunt resistor, which converts the current flow through it to a voltage drop. We then use a 24-bit ADC to read the voltage drop and supply the microcontroller with the voltage drop value of the shunt resistor. The microcontroller then sends the data over SPI bus to the 7-segment LED display drivers, which drive the LED pixel display. The microcontroller is also connected to the non-volatile memory for data storage. All of this is then powered from the vehicle's onboard power through a contained power supply. This is the description of the level 1 functional diagram components. Most important component here is the high resolution ADC, because the voltage drop of the shunt resistor is very small, which helps keep the power dissipation low. And so the ADC has to be very high resolution to read such a small voltage drop.
Here's our level 2 functional design that shows how our power supply will work within our circuit. It will take 12 through 15 volt DC power that will go through a smoothing filter to smooth the DC voltage. That will then go into a step down converter to convert the power down to 5 volt DC, which will then go into the rest of the circuit and power everything up as you saw before. Here we break down the modules for the power supply from the last slide. The smoothing filter will have an input of 12 through 15 volt DC, and the output will be a smooth DC voltage, which is effective since cars are noisy. The step down converter module will have the smooth DC voltage and convert it to 5 volt DC for the circuit, as I said before.
This is the alternate design we considered, which is the Hall effect sensor. We decided against it because it is sensitive to ambient noise, of which there's a lot in a running engine compartment. It is also inaccurate at low currents, and if the engine is idling with no high power equipment running, current draw is very low.
Here's our flow chart, which shows the flow of our system. When it starts up, the display will turn on. If not, it will restart. Once on, the shunt resistor will have a current flow through it that converts into a voltage drop into the ADC. The ADC is powered by the 12 through 15 volt DC power supply that has a filter and a step down converter to get 5-volt DC out into the ADC, the non-volatile memory, the microcontroller, and the LED driver. From the ADC, it will read the voltage drop and send out the signal into the microcontroller that then sends the signal into the 7-segment LED driver and to the non-volatile memory for later use. This will then end the system and or repeat the process if started again.
In this activity diagram, you can see that we will be using a dual core microcontroller with one core running the display and the other core reading the ADC at a predetermined interval.
All right, here's our work breakdown structure where you can see how we will go about breaking up the work into different sections to finish our project on time. First, we will design the circuit of the ammeter and order the components. The next section in 1.3, we are going to construct, test, and integrate the power supply, the shunt resistor, and the 24-bit ADC into the circuit. As you can see, we continue with our breakdown for the work for the class. We know now we'll be testing, constructing, and integrating the LED driver, the non-volatile memory, and the microcontroller into the circuit. Lastly, you can see the last bit of our work breakdown here, and we will have complete the system integration and testing phase to get ready for the end of the course. And we are giving ourselves about 1 to 15 days to complete system integration and testing, just in case if there's problems and we need to go back and fix those bugs.
This is our Gantt chart that shows the order which we're going to complete all the tasks. The main part of this would be the interface circuitry and the microcontroller integration.
All right, so we have looked up some parts, what we think that we might need. So here's an estimated cost of what it might come out to for the materials. And then there is our labor cost. There's 2 of us, and the average monthly salary of an engineer is about 5,000. We're only gonna be doing this for 2 months. So once we did the math, yeah, we came out to about that.
In summary, we propose a refresh to the current generation of ammeters. Our ammeter will bring this useful piece of equipment into today's level of technology and provide detailed information for the user.
And then here's our references for our project so far. All right, and that is our project for our capstone class.
Thank you.